Hello and welcome to The Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. If things seem a bit out of sorts today, it's because the episode we planned last night had to be largely tossed out the window due to large breaking science news. This doesn't happen very often to us, but well, a pair of black holes were caught eating a pair of neutron stars, and this is kind of the astronomical equivalent of if it bleeds, it leads. We'll be dedicating our second segment of the show to that event. For now, let's visit a few of today's planned stories.
My senior year of high school, back before I really knew volcanoes would one day play a huge role in my life, Mount Pinatubo erupted in the Philippines. This explosive eruption came from a previously non threatening and very eroded volcano that was covered in dense forests and, unfortunately, a whole lot of humans. While highly memorable, this massive eruption has nothing on the long term danger posed by nearby Indonesian volcanoes. Merapi on the island of Java, in particular, tends to explode more like a high school science project than the gentle oozing volcanoes we see in Hawaii and often in Iceland. Researchers looked at the chemical mix of tiny minerals formed in the lava to understand what exactly makes Merapi so explosive. And the answer is carbon dioxide gas. According to Valentin Troll, a co author on the study, Merapi's magma interacts intensively with Earth's crust before erupting. That's highly important because when magma reacts with, for instance, the limestone that's found in central Java right under the volcano, the magma becomes full to bursting with carbon dioxide and water, and the eruptions get more explosive. For those of you who may not have made fake volcanoes in school, the mix of vinegar and baking soda that is used produces carbon dioxide and water. Exactly what is in this volcano. The thing is, in the volcano, it's mixed with molten rock instead of red food coloring. The horrible chemical reaction is thanks to that composition. There are place to place variations in the Earth's mantle where magma originates and in the Earth's crust, which the magma travels through. Beneath Java is the chemistry of explosive volcanism. Understanding what's going on won't bring back the lives lost to Merapi, but hopefully will help us understand what future behavior to expect. This work appears in Nature Communications and was led by Francis Deegan.
From exploding volcanoes, we now turn to exploding stars. In looking at the ways in which stars die, there are two basic scenarios. Stars like our sun eventually just sort of peter out as they run out of fuel in their core and stop creating energy via nuclear reactions. The light those reactions had been producing had been supporting the star against collapse under its own gravity. But in the absence of light, that core in these smaller stars will collapse into a tiny moon sized white dwarf star, while the remaining atmosphere, if there is any left, it drifts away. This is how the majority of stars will die. In a few instances, however, the collapsing core is so massive that instead of just hunkering down into a smaller object, it also explodes. This can happen in a couple of different ways. If you pile a bunch of extra matter from a nearby star onto an already collapsed white dwarf, it will explode as a Type 1a supernova. If you have a truly giant star, greater than 10 solar masses in size, it will collapse and the core will become either a neutron star, a black hole, or nothing but energy, as things around it explode in the collapse. Now we are learning a theory on a third way for stars to die may be true and may be able to explain the death of the star that formed the Crab Nebula. This third form of death is electron capture collapse. Elderly red superasymptotic giant branch stars can reach a point where they stop having nuclear reactions and their core starts to collapse. And the ionized oxygen, neon, and magnesium grab onto all the free electrons and suddenly get tiny by forming atoms. This is the atomic difference between everyone taking their own car to work and taking a rideshare. As soon as all those particles combine, they take up a whole lot less space, and infalling material around them, it ends up going supernova. While theories about this kind of explosion had existed for a long time, including theories that explain Chinese observations of the Crab Nebula's birth in 1054, modern observations didn't exist until now. In 2018, a weird supernova whose progenitor star was observed to be a super asymptotic giant branch star in surveys was seen to explode. Careful observations of how that explosion evolved over time matched the electron capture supernova theories, and also taught us there are apparently more than two ways to explode a star. This work appears in Nature Astronomy and was led by Dachi Hiramutsu.
Super asymptotic giant branch stars. I want Pamela to say that 10 times fast. While not actually explosive, our third story somewhat continues our theme. While using the new Cheops Space Telescope to study a known planet orbiting the star Nu 2 Lupi, a weird dip in brightness was observed that could only be one thing: an additional planet. Okay, it could have been a whole lot of things. But by using archival data of this star system, researchers were able to determine that a third planet in the system had photobombed their images of the second planet. This planet has a roughly 107-day orbit and is at a distance from its star where we are only beginning to find planets. The system is less than 50 light years away, and with telescopes like Hubble and one day JWST, we may be able to measure all these worlds' atmospheres. According to Cheops project scientist Kate Isaac, while none of these planets would be habitable, their diversity makes the system even more exciting, and a great future prospect for testing how these bodies form and change over time. There is also the potential to search for rings or moons in the new 2 Lupi system, as the exquisite precision and stability of Cheops could allow detection of bodies down to roughly the size of Mars. This work appears in Nature Astronomy and was led by Letitia Delrez. After the break, we'll be back to talk about hungry black holes and how they shook the space time continuum eating their dinner. Stay tuned.
Continuing our theme of destructive destruction, we'd like to introduce you to GW 200105 and GW 200115. These two gravitational wave detections, just 10 days apart, originated from the mergers of pairs of black holes and neutron stars. Detected by the LIGO and Virgo detectors, these discoveries allow astronomers to essentially lay down a royal flush of detections. In September 2015, LIGO and Virgo made their first observations of a pair of black holes merging and sending gravitational waves rippling through the universe, where they would be detected as oscillations in the space between detectors, as space literally expanded and contracted in reaction to this event. Just like different bells produce different kinds of sounds, and you can measure the size of a bottle by the kind of sound it makes when blown into, the size of merging objects can be measured by the gravitational waves they make in the space-time continuum. Yes, folks, you, like the detectors, expand and contract by ever so small an amount as these waves pass through you. These waves are tiny and comparable to the size of a particle, not to the size of a person, and we'll never notice them with our senses. And it is frankly amazing we can detect them at all. I have to admit, I didn't think we'd be able to ever make these detections from Earth, but determined scientists and engineers have a habit of finding a way. From that first black hole merger, LIGO and Virgo have gone on to make numerous discoveries, including the August 2017 first discovery of two neutron stars merging. When it came to generating detectable gravitational waves, there aren't a lot of options out there. Two neutron stars can do it, two black holes can do it, and the combo of a neutron star and a black hole, they are detectable too. A quick literature review was unable to find a paper on the detection of any existing black hole neutron star binary systems, although one 2005 paper led by Eric Fall postulated they should be very rare, with one being born only once per 10 million years or less. They also should only last for about 100 million years before they merge. This means they are rare and short lived and number among the hardest things to observe. Although a paper from 2020, led by Debatri Chattopadhyaya, indicates that the square kilometer array may be able to start detecting them if Meerkat doesn't find them first. But it turns out LIGO and Virgo wanted that gold star. That final detectable pair, the black hole neutron star combo, has been seen not once, but twice at the moment of their merger into an even bigger black hole. Royal flush. That makes black hole found in 2015, neutron star in 2017, and now black hole neutron star merger found in 2021. The two of these were seen in 10 days may seem a bit hard to fathom, but this is in part due to the ever-improving abilities of the detectors and the fact that random events sometimes will occur one after the other. Now that LIGO and Virgo can detect these, we look forward to seeing more and more combos of more and more different sizes and orbits as these objects merge and shake the time and space continuum. After the break, we'll be back with a side journey to Mars before we continue today's theme of destruction with a look at asteroids and their habit of shaking our world. Stay tuned.
We talk a lot about water on Mars here on the Daily Space. It's an important topic. With plans underway to send humans to the red planet, scientists and engineers are concerned about how to provide necessary resources for a prolonged mission. Water is heavy and fuel is expensive, making it better for everyone involved if water is already on Mars, accessible, and relatively easy to make drinkable. Recently, there was research that came out that said the South Polar ice caps had liquid lakes of water underneath the surface. They were discovered with bright radar reflections taken using the Mars Advanced Radar for Subsurface and Ionosphere Sounding, or MARSIS, an instrument aboard the ESA's Mars Express orbiter. These lakes likely have a lot of salt dissolved in them, making them more briny than clear and not easily drinkable. Still, subsurface liquid water would be fantastic for crewed missions to be able to access all that necessary life sustaining fluid, even if it had to be purified first. But if there is one thing we know about space anywhere off our planet, it is not friendly to biological life. So before we send people off to a distant world, even one in our own solar system, we want to make absolutely certain that what we think is water is actually water. And in new research published this week in Geophysical Research Letters, a team of scientists led by Carver Beerson and including Planetary Science Institute's Dan Putzig examined the data previously collected by MARSIS. Using a different analysis method than the previous paper, they concluded that, well, there are other materials that could explain that bright reflection. Put simply, the previous method involved how a material responds to an electric field. That led to the conclusion that liquid water caused the bright reflection. The new paper looked instead at how much electrical current the material could carry, using ice sheets here on Earth as analogs for Mars's polar ice. And the results showed that the reflection could be due to clays, metallic minerals, or even salty ice. These results do not rule out the possibility of liquid water, mind you. They just mean that we cannot always make a confident decision based on one possible analytic method if there are other methods available. Think of it this way: just because you see the glint off of a rock in the distance doesn't mean you found gold. So before you bring all your mining equipment over, you want to make sure you have found the right mineral. Or, as Than reiterates, because water, particularly in a liquid form, is so important to sustaining life, seeking out where it may exist on Mars today or in the past is of paramount importance to astrobiological studies. Ensuring that we fully consider other possibilities for reported detections of liquid water is crucial to the scientific process. Now, Pamela will be back in a moment to focus on how to survive on Earth, unlike the dinosaurs. It's almost Asteroid Day, everyone. Stay tuned.
In 1908, in middle of nowhere Siberia, a fairly large object streaked through the sky and exploded over the eastern Siberian taiga. This air blast is estimated to have flattened 80 million trees, killed countless reindeer, and 3 humans. And it created a shock wave through the atmosphere that was detected all around the world. This was the Tunguska Event. Tomorrow, our show will be highlighting the launches and history of rockets, so we're going to talk about that June 30th event today instead. Asteroid Day is a new UN-sanctioned yearly event held on the anniversary of that bad day in Siberia, and it is a day on which scientists and science communicators work to remind everyone that rocks can still fall out of the sky and kill. Tunguska isn't the only human-observed major event. For many of you watching now, the 2013 event in Chelyabinsk was a wake-up call to just how dangerous a 20-meter space rock can be. Streaking through the early morning sky and observed in security and dashboard cameras, that event included an explosion above the ground, a massive shock wave, and a fair amount of destruction. We are pleased to share that no reindeer are known to have been harmed and no deaths were reported. Now, the reason that these kinds of objects explode is they are either rocks or ice predominantly that are mixed with either ice or rocks. And when that ice gets hot, it melts and expands. And when you have expanding gas inside of something largely rocky, it explodes. And this is bad because it can flatten large areas. Now, depending on how things strike and where things strike, may be better or worse than the ground getting hit. Either way, we want to know about these things before they actually happen, and this is where the B612 Foundation comes in. Named after the asteroid of the Little Prince, 46610, B612, which in hex is B612, this society is out there looking to encourage research into how to defend ourselves. Missions like Dawn, OREX, and Hayabusa allow us to study asteroids, and future missions may help us learn how to move asteroids. Until we have that tech, however, we need to watch the asteroids to make sure we know when the next big one might be coming. Let's hope that day is far in the future. Until then, this has been The Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.